Indeed.
Good afternoon, everyone. A very warm welcome to today's webinar. We are here today in the webinar Carbon Capture, Utilization and Storage in Action, Intensified Capture, Renewable Technologies, Ethics and Regional Challenges. So this session today is proudly brought to you by the Reuse Project, a Horizon Europe initiative. And we are truly delighted to have all of you here today with us. And thank you very much for choosing to spend your time with us today. And we hope you will leave this session with valuable insights, thought-provoking discussions, and maybe some renewed perspectives. Let me emphasize that a little bit before we start the webinar today, that this isn't just a one-way presentation today. Today, we are meant to be a two-way exchange, a platform for interaction and shared knowledge. So we hope to have your active engagement, especially in the Q&A sessions. So please feel free to use the Q&A box to submit any questions that you would like to be answered live by our speakers. But for general comments or conversation, please use the chat. So yes, just to reiterate a little bit, please use the Q&A box for any questions that you want to be answered live today. And please use the chat meanwhile for other engagement. So now I would like to give the stage to Dr. Sakis from the Center for Research and Technology-Hellas, the coordinator of the Reuse project, to start the webinar.
Thank you, Lynn. Let me share my screen. Okay, I hope you can all see my presentation. So, my name is Athanasios Sakis Papadopoulos. I'm a research director at the Center for Research and Technology-Hellas in Greece. And I'm here in my capacity as a coordinator of the project to give you a presentation, an overview of what the project is about. This is a project funded by Horizon Europe. It has been funded in response to the call for development of carbon fixation technology for biogenic flue gases. The full title of the project is Enzymatic CO2 Capture in a Rotating Packed Bed and Electrocatalytic CO2 Reduction to Useful Products. And we are a consortium of several partners, research organizations, and companies across Europe. First of all, I would like to talk about, mention a few facts about CO2 emissions. In the 1950s, the world was emitting about 6 billion tons of CO2 per year, but this has escalated to about 35 billion tons per year. Europe's contribution as of 2023 was about 5 billion tons per year. We see here in this graph, I found very interesting, that's why I added it in my presentation, that Europe, USA, America, and Africa and India exhibit a slow decrease that has been more pronounced after, let's say, 2020. On the other hand, it seems that China and Asia are emitting a lot. Their emissions are increasing with a high rate. So it kind of seems that, policies, especially in Europe, that mean to reduce CO2 emissions seem to be, taking place and seem to be bearing results, but still we have a long way to go. So in the EU, they have signed this European Green Deal, the European Commission, which establishes the objective of becoming climate neutral in 2050. So the objective requires a greenhouse gas emissions reduction of 55% by 2030 And this in turn requires significantly higher shares of renewable energy resources. We need to do more, obviously, and so biomass derived emissions, biomass is going to play a big role in terms of reaching these goals in the coming years. It's a key energy carrier. Biomass combustion systems may enable the decarbonization of various sectors as they allow for highly efficient use of sustainable biomass residues, and the combination of biomass with carbon capture and utilization of storage can result to net zero negative systems. And you see here in this figure how the use of CCS can contribute to this end. Now, the question is, how can we capture CO2? There are various technologies. First of all, there are three different categories, mainly pre-combustion, oxy-fuel, and post-combustion. So in this project, we are involved in post-combustion capture, and for this, there are also other several technologies, so solvent-based absorption, calcium looping, membranes, adsorption, algae. So all have pros and cons, and we will, in the end, we will use, as a society, we will use all these technologies depending on the flue gas composition and the meeting plant requirements. Our project is focused on solvent-based absorption desorption. You may already know that solvent-based absorption desorption is performed in packed bed columns. These large columns, they can reach several meters in height, 20, 30 meters in height, and they may have also large diameters. So you have the CO2, the flue gas that comes in contact with the solvent, and then you need to heat it up in order for CO2 to be released and for the solvent to be recycled. The advantages is that this technology is well established and easy to meet the conditions, and also it's easy to retrofit onto existing plants. It's chemical absorption. It is a very well-known process in industry. On the other hand, this technology has high capital costs and large energy penalties. Part of the reason for this is the use of monoethanolamine as a solvent. This is a reference solvent. This is how it all started, and this is what everybody is using in order to compare their solvents and the new developments, and has some disadvantages. And of course, we need new and considerably improved solvents and processes. Now, current research and current development efforts focus on four main types of flow sheets in order to reduce these costs. The flow sheet that I showed you is the standard one. There are a lot of large-scale pilot plants at high TRL that are based on this flow sheet, but with some modifications, obviously using some more advanced solvents, but also implemented energy recovery measures. There are other type of new solvents that are being tested and developed at a larger scale and tested at a larger scale. These include the so-called phase change solvents, where what happens is that the single liquid phase solvent separates into two liquid phases like oil and water, and then you have one liquid phase that is rich in water and solvent that can be recycled back to the absorber because it has very, very little CO2, so it doesn't have to go through thermal separation. And there is another phase at the bottom that is full of CO2 and has less water and solvent. So this is the only part that goes through to thermal separation, and so this enables reduction in costs. And of course, there is this technology here, as you see. This changes completely the operating rationale. It's called a rotating packed bed. It's a highly intensified equipment. So instead of relying on gravitational forces to move the solvent from the bottom of the absorber from the top of the absorber to the bottom, you have spinning here, very intense spinning, which intensifies mass transfer, and you can actually achieve the same efficiency, but with much, much smaller equipment in terms of volume and space footprint. And of course, when we capture CO2, we want to do something with it. We have to do something with it because no matter how much we reduce the cost here, there are still costs. So we want to be able to make some revenue. There are different ways of doing that: enhanced oil recovery, put the CO2 into building materials as salts, derive fuels, chemicals, or minerals, produce fuels, chemicals, or minerals. What this particular project focuses on is electrocatalytic technology. So basically, the production of fuels and chemicals can be performed thermocatalytically, electrocatalytically, or even photocatalytically. We're focusing on electrocatalytic technologies because they may use renewable energy. I believe they are slightly more mature than photocatalytic ones, and on the other hand, they may require considerably milder conditions than the thermocatalytic ones. But there is still a lot of scope for development. So there are different ways of connecting the capture and the utilization process. So imagine a system of absorption and desorption with columns. What one can do is capture the CO2 here and then put it as a gas into the CO2 reduction cell where you can actually produce your product. The problem here is that if you do reduction in gas phase, this has high kinetic barriers and low efficiency. And of course, you need hydrogen to come from a different equipment, an electrolyzer, for example. You can also put the CO2 into the liquid phase, into water here, but CO2 is hydrophobic, so the solubility is very small, so you still need a lot of excess CO2, and this reduces the efficiency. Another approach would be to directly put the CO2 as it is captured with in the solvent. You can put it directly into the CO2 reduction cell, and then you can you can remove it from the solvent through the electrical fields that are generated here. You can get your product and you can recycle the solvent. So the advantage here is that the solvent is generated simultaneously with CO2 reduction products. There's no need for the extra thermal generation step. So you save energy, but you also save equipment costs. And then you can directly use renewable energy here. The electricity can come from renewable energy. So the reuse idea is very similar. We're using this, what we call direct CO2 capture and CO2 reduction, but instead of having a typical absorber column, we have a rotating packed bed for CO2 absorption, and we also have specifically a packing material in the packed bed that uses an enzyme, and I will explain why this happens. And then you can have your CO2 into the solvent, go and produce your product. Of course, there are other advances that I will explain, and we also have biomass gasification here as our flue gas source, and we have pilot scale facilities where we're going to do some research and also demonstrate all the systems. The key innovations are the use of the rotating packed bed. It has short residence time, 15 to 20 times lower volume, fast mass transfer, low space footprint. You see one here that has been developed by the University of Newcastle. It's a 1 ton per day case, and it's very efficient. Now, normally, you would need to have a solvent that exhibits fast kinetics in the absorption in order to capture the CO2 in this small scale. Instead of using such a solvent, we're using what we call biomimetic absorption with carbonic anhydrase. This is an enzyme. Theoretically, it has 4,000 times faster CO2. It enables 4,000 times faster CO2 hydrolysis compared to the monoethanolamine solvent. So it replaces the solvent that exhibits the fast kinetics. So you still need some solvent, but not as much as you would normally need. And another advance here in this project is that the CA enzyme will be immobilized on a fiber that is needed on the packing material. So it's a very intensified system. Another advancement in the project is that we're going to combine this with a phase change solvent. So the idea is that with this solvent, we'll be able to deliver much more concentrated CO2 into the CO2 reduction cell than we would normally deliver with a conventional solvent. Other key innovations include the design of the CO2R cell itself. We're going to design a zero-gap membrane type flow cell to reduce ohmic losses by decreasing the interelectrode distance. We're going to design functionalized carbon surfaces, utilize carbon materials with different morphological nature via plasma. We're going to design template-free, shape-controlled, tin-based catalysts with or without dopants via plasma, electrochemical routes on functionalized carbon surfaces that favor selectivity towards formic acid, which is one of the products that we're targeting. The other would be carbon monoxide. Finally, we'll have some advances in the gasification. So we're going to design and test advanced catalysts for tar abatement. We're going to develop strategies and test in order to address variability in biomass gasification. And we're going to do the test combining biomass with waste. So this is it from me. Thank you for your attention. And I give the floor to the next presenter.
Thank you, Sakis. Meanwhile, everybody, if you have any questions, please, again, feel free to input your question in the Q&A box so we can answer afterwards. Jonathan?
Yep, okay. Hello, everyone. My name is Jonathan Lee. I work at the University of Newcastle in the UK, where I'm a professor of carbon capture. I have worked mainly in the past on using rotating packed beds to intensify carbon capture processes. And today I'm going to talk about the role of CCUS in climate change. So I'm not going to talk specifically about climate change because we all know it's going on. And as this slide shows, we've known that it's been going on for a very long time. This is from March 1912, when they estimated we were producing about 7 gigatons a year of CO2 from burning coal, mainly then. Back then they knew from the work of Arrhenius that that was going to lead to the temperature of the Earth rising because of the radiation being reflected back from the CO2 in the atmosphere. And it notes that it may be considerable in a few centuries' time. Well, we're a century and a bit later on, and it is very considerable, the effect that injecting all that CO2 into the atmosphere has had. And the basic science which says the Earth is going to warm as you put CO2 into the atmosphere has been well known for over 150 years. Europe emitted about 3.6 gigatons of CO2 in 2022. We talk about CO2 equivalent, that includes CO2, methane, which comes mainly from hydrocarbon production, nitrous oxides, which come mainly from burning fuels in engines, either jet engines or internal combustion engines. Some nitrous oxide comes from the land, and then finally fluorinated gases, which come mainly from refrigeration systems. So the CO2 split, the biggest proportion is energy supply. So that's burning gas or coal to produce electrical energy. The next biggest portion is transport, from basically cars and lorries, and then the next one after that is industry, which I'll break down in a bit more detail. Other uses are domestic heating, and agriculture, and international aviation and shipping. Now, at the moment, the plan is that the energy supply will be converted entirely to green sources, either wind, renewables, or sorry, not green sources, carbon-free sources, renewables or nuclear, and we produce all that electricity, which will basically let us eliminate use of or emissions from transport. So that's the plan going forward. That leaves industry, which has got these hard to abate point sources, and although industry is moving towards electrification, there are some industries which can't be abated. So these are some of the examples. So a large source of emissions is the manufacture of cement for building materials. We take limestone and we remove CO2 from the limestone to produce the basis of cement. And to do that, we need to use a lot of heat as well. And so cement manufacturing produces a lot of CO2. And we end up with a flue gas, which is roughly 18% CO2 leaving. Another big source of CO2 emissions is steel manufacturing, and the emissions here are just from the fossil fuels we burn to heat the process, and we end up with a flue gas of around about 22% by volume. And then another growing source is where we're converting our waste into energy, which is a perfectly reasonable thing to do. But we do produce a flue gas, which is around about 10% CO2. So if we're going to reprocess waste into energy, then we do need to capture that CO2 that's coming from it. Because the chances are some of it had a fossil source in the first place. Now you may notice under all these pictures, there are some E-min numbers. So what those numbers are the minimum energy that we have to put in to this system to capture the CO2 from these sources. So if we did everything perfectly from an energy point of view, then to separate the CO2 from the flue gas, we'd need that amount of energy, which is not insignificant. And I just want you to bear in mind these numbers for later on in the talk. Now, just to bring something to your attention, there is a lot of talk about direct air capture, where we capture CO2 in the atmosphere and use that either for producing chemicals or actually to put it in the ground. So we do something called negative emissions, where we remove CO2 from the atmosphere. The minimum energy for that process is 0.5 gigajoules per ton, which you can see is between 2 and 3 times what we need to put in for these point sources from industry. So if we're going to do direct air capture, we have to be extremely careful on the energy use of the processes that we're using. Now, I want to spend a bit of time on this slide because it really highlights the need for carbon capture and storage, really. So this was produced by Professor Miles Allen from the University of Oxford, and he showed it first at the Greenhouse Gas Technologies Conference last October in Calgary. And it's him and his team basically collecting data from the IPCC reports about what's possible from different methods of carbon capture, and then producing this graph. Now, the first line to look at is this black or dark reddish line that's running from the top left down to the bottom right of the graph. And you'll notice that that sits just shy of 40 gigatons per year of CO2 at the top left corner. That is currently where we are. And we're doing virtually no carbon capture. And so we're not stopping global warming as it stands. In fact, we're increasing the amount of CO2 that we produce at the moment. The green line is what we can get from nature in terms of removing carbon from the atmosphere. Now, these are called nature-based solutions. So these are engineering solutions, but using sort of natural systems. It might mean mining certain types of rock and spreading it on the land. It might mean sort of promoting peat bogs in the UK, but its potential to capture CO2 is really quite limited. Okay. The blue line is basically what's planned or projected for carbon capture and storage. So that's an engineering intervention, and that's what we can achieve. And then this dotted line at the bottom is what the biosphere, which is the oceans and existing plants, can achieve in terms of CO2 removal. Now it's rising towards zero because basically the oceans are starting to fill up with CO2 or dissolved CO2. And so the red line is what we end up with when all those things are making their contributions towards removing CO2 from the atmosphere. And this is the CO2 that stays in the atmosphere and causes global warming and or climate change. And so we need, what this shows is we definitely need carbon capture to even get this line coming down, because we're not going to do it from the oceans. We're not going to do it by nature taking up CO2. We are going to need some form of carbon capture. And you can see that's not getting to zero, that red line. And the plan is to have net zero by 2050. And that's our target. And that red line should be doing that. To go from 2016, when the Paris agreements were signed, to 2050, when we're doing net zero emissions of CO2 into the atmosphere. So you can see that this red line, based on current predictions, is going down, but it's not going down nearly fast enough. So what is carbon capture and storage? Very quickly, we take CO2 from an industrial source, be it power generation, though hopefully that won't be the main source, or industry. We capture it somehow, and then we end up with CO2 gas. That CO2 gas is compressed and sent most likely offshore, particularly in the European context, that will be offshore, and it is sent to some sort of reservoir. That could be an old gas field, or the intention is more likely to be in what's called a saline aquifer, which is a geological feature, a bit like a hydrocarbon field that exists. There are a lot of them existing in the North Sea. CO2 capture is not enhanced oil recovery. It's not storage enhanced oil recovery. It produces CO2, and so shouldn't be considered as storage ever. But just looking in a bit more detail at the capture, so gas fields, yes, we can put CO2 into them and we can fill them up with CO2 and then seal them. But saline aquifers are more interesting and a better long-term solution, and we'll just see why. So basically, in a saline aquifer, we've got a cap rock, and we inject CO2 under that cap rock into the saline aquifer, where there's basically salty water. And the CO2 is trapped by a number of mechanisms. There's physical trapping, which is by the actual cap rock. There's residual trapping, where the CO2 is actually trapped in the pores of the sandstone. There's solution trapping, where the CO2 is dissolved into the water. And then there's mineral trapping, where that CO2 over time actually turns into solids, normally carbonates. And basically in a saline aquifer, we're hoping that we can, that over time in saline aquifers, we'll get solution trapping and mineral trapping increasing and residual trapping. And so we have to rely less on the actual physical rock to trap the CO2 permanently. And that's why we're interested in injecting into saline aquifers. Now, CO2 capture at large scale has been done already. This is the Boundary Dam power plant, which went online in 2015. The power stations on the left, the big process on the bottom right of that picture is the carbon capture process. And they're capturing 2,400 tons per day of CO2 from a 115 megawatt power station. Now, unfortunately, most of that goes for enhanced oil recovery in Alberta, but you know, this is significant because it's shown that it's possible to do this at a very large scale. Now, just coming back to some of the methods that Sakis mentioned in his talk, here we're comparing solvent-based carbon capture, adsorption onto a solid, membrane, chemical looping, and microalgae. And we're looking at the cost and the energy consumption and some comments on them. Now, solvent-based adsorption adsorption onto a solid and membrane have been, all these methods have been heavily investigated. Solvent-based is the most well known, and its cost and energy consumption depend on the solvent used and the equipment that you're using. The solid adsorption and membranes, their cost depends really on the price and lifetime of the adsorbent or the membrane, and the energy consumption depends on the pressure that you need to use. Chemical looping, it uses a very low cost absorbent and potentially is a very attractive method, but there are still some technical issues with it. And then microalgae is a very attractive method from an energy point of view, but has a very high cost because you have to keep growing microalgae all the time, and that costs a significant amount of money. So we deploy solvent-based carbon capture because it's been proven to work at the scales required. I mean, that's why at the moment most of the processes that people are deploying, like Boundary Dam, are based on using a solvent. Now, when we get to utilization, the basic idea is we've got a carbon capture and storage chain where we capture, compress, transport, and store it. We take some CO2 from after the capture stage, and we combine it with some chemicals, and we get some products. And Sakis has already talked a little bit about what those products are. The one caveat with it is that if you're going to have CO2 from a fossil source that's being converted, then the products that you make must have a significant lifetime, at least 5 years, preferably hundreds of years. And so some good examples of things that you might convert your fossil CO2 into are building materials and plastics. You should never convert fossil CO2 into fuels because you're going to re-emit that CO2 fairly quickly after you've produced the fuel. Now, in the reuse project, we are basically combining the capture and utilization because we're doing some reaction in the same places we're doing the capture, and then we're doing some processing of those chemicals further downstream. So we're intensifying CO2 utilization not only by the equipment that we're using, but by combining processes. And the rotating pat bed is this key technology. So a rotating pat bed is basically some packing material, which is shown on the right here in a sort of disc form, and that spins around typically between sort of 600 and 1500 RPM at this scale. And the liquid is injected into the center of that packing and flows out radially. The gas flows in from the outside, and we get the liquid and gas flowing past each other and transferring, in this case, CO2 between each other. Because it's rotating, we can get more gas and liquid through it for a given volume of packing. And because it's rotating, the mass transfer process is much faster. And so we can get volume reduction by 20 to 50 times. 50 is very optimistic, but it's been measured. And because we shrink the size of the unit, we basically get a massive capital cost saving, which can be up to 40%. So that's the rotating pat bed. In the reuse project, we are basically going to have a rotating pat bed where we have sheets of the packing material coated with a biocatalyst. So we'll make a stack of those and then bolt them all together, and that will be our rotating pat bed. And the idea is that we're going to convert CO2 and carbonate into CO2 into carbonate and bicarbonate ions that we can then use to make other chemicals. So that's what we're going to be doing in the rotating pat bed. Now, this idea of making carbonate ions in a rotating pat bed has already been proven by this project called Carbonation, which we did with Procter & Gamble and the Centre for Process Innovation in the UK. And we use spray dryer off gas, which has a very low CO2 concentration, around about 1.5% CO2, to produce solid carbonate in a one-step process. And that was demonstrated in Sheffield earlier this year. So we definitely can do these sorts of things in rotating pat beds, and that's what we're going to do with the reuse project. Okay, well, thank you for your attention. Any questions, if you put them in the chat, I'll answer them.
Thank you very much, Jonathan, for your presentation. I saw some nice questions coming in and also some live answer from our speakers. So everybody, please, if you have any questions, please feel free to input in the Q&A box. Meanwhile, we'd like to welcome Dr. Stella from CERTH to continue with our webinar.
Thank you, Lynn, and good afternoon, everyone. My name is Stella Balomenou. I'm a research director at the Chemical Process and Energy Resources Institute of CERTH in Greece. And it's my great pleasure to be here today, part of this exciting workshop and part of reuse project. My presentation will be on this. I will just start sharing. And so you will see that it's on this nice U of the, I hope you can see in full screen. Great.
Yeah, now
So,
yes.
Thank you. So it's on this U from the CCUS, which means the utilization, the use of CO2 as a raw material and feedstock for the production of valuable chemicals and fuels with various processes. And I will focus today on the electrochemical processes to upgrade and recycle CO2. I'll skip this one. So the argument has been heard, but let's make it a little bit stronger. If you consider what is the annual production of CO2, which is around 24 gigatons or more, and what is the annual demand based on the use for either production of chemicals, primarily fertilizers, urea and fertilizers, or the rest of the needs having to do with the physical properties of CO2, like enhanced oil recovery, preservative and beverage additive, fire suspension, suppression, coolant, or solvent, we see that there is a lot of CO2 we can use. And if we discuss energy vectors, and we see what are the requirements for suitable ones, these are listed here. Even if we focus on this last part, which is very, very crucial, and we consider vectors like hydrogen, which primarily meets this aspect. However, if we see in this figure here to the right, all kind of fuels, liquid, gaseous, including hydrogen, also batteries as a storage means of electrical energy, we can see that sea-based vectors, the traditional probably liquid fuels, probably fulfill all the requirements listed here, apart from this greenhouse gases emission. So having in mind how much CO2 is available and how such kind of fuels or energy vectors are really fulfilling requirements for energy density by weight and by volume at the same time for large-scale applications, we see clearly here that it's preferable and suitable and sustainable to find solutions to recycle CO2 and produce renewable fuels by using renewable energy rather than develop completely new energy vectors. So the case is clear and is here. By processes to convert those CO2, there are several processes considered or being studied or trying to reach higher level of application. I list here the different variants, starting from stoichiometric, thermochemical, biochemical, photocatalytic, depending on whether the energy is, whether some external energy is required and at which form this is provided to the different processes. So in this case, no external thermodynamic energy inputs are needed to drive the reactions. These are driven by the chemical potential of the system. Thermochemical reactions, which take the required energy, the external energy from heat, which comes from concentrated solar systems to meet this usually two-step reaction where a metal oxide is reduced in a first state, is used for the production of syngas usually, and through this second part, which reoxidizes the metal, has a recycling kind of process. Biochemical processes, which are of high interest because it's a very nice way to produce biofuels like from microalgae. However, we have to consider in this case that these processes suffer from very low efficiencies. They are quite low and almost 1%. So they have to meet like a 10% range to be viable for commercial and plant application. Photocatalytic reactions, here you have a catalyst which is irradiated by solar light, and this is the energy, thus is how the energy is provided for the catalysis to take place. A different variation, the photoelectrochemical, where the catalyst now is in the form of an anode and cathode electrode. It's formulated in such a layer. Semiconductors usually play this role. And although there are high offers in, and high, let's say, advantages in this system, some photo corrosion problems having to do with the stability of the semiconductors in the specific applications present some issues that need to be tackled. I have left electrochemical processes as the last one, which is the center part of my presentation. So in electrochemical processes, we need to have, again, a catalyst or electrode in this case, in a certain configuration of a cell, and the electric energy is the energy is provided as electric energy to reduce CO2 into the desired products, chemicals, maybe also fuels. So some essential, some important information about electrochemical CO2 cells and for the CO2 reduction. So a typical simple example is shown here by a cell having two electrodes, anode and cathode, and two compartments, anode and cathode. The cell is fed with an aqueous, let's say, electrolyte solution. And the two compartments are separated by a proton exchange membrane, a membrane which allows the travel only of protons through its, let's say, structure. So in the one side, in the anode side, water is splitted into hydrogen and oxygen. Hydrogen in the form of protons travels on the other side and meets CO2, which is diluted. It's a CO2 saturated electrolyte in the cathode side. And there it can meet the CO2, the protons, and you can have the cathode reaction as shown here. The anode reaction is the water splitting. And this is the overall reaction which leads to CO formation. However, we have to consider that CO2 towards CO is not the only reaction that takes place. Also, hydrogen, when it reaches the cathode side, it may form hydrogen, gas hydrogen. The hydrogen evolution reaction actually takes place, the one that is shown here. So it also comes out of the cathode compartment. So this is a competitive reaction, and we have to take into consideration when designing or operating such systems. So CO, hydrogen was the, let's say, competitor. However, CO is not the only thing that can be produced in such a cell. A list of other compounds are shown here. And for each and one of them, there is a certain, let's say, demand. Thermodynamics is indicating this demand. And this is actually the electrical energy input required in order for any of these reactions to be done. Apart from the thermodynamics, kinetics also plays an important role. because in order to have reasonable amounts of the products in any of the cases, you need to overcome some the losses or difficulties or imperfections, what we all know as an activation overpotential and overall overpotential. So you actually need to sacrifice more energy, higher potential than what is listed here for the thermodynamic one, in order to really have a system going. So in this precise point, we have to consider that these overpotentials define actually what will happen. The difficulty into or the level of overpotential is indicated by these different, let's say, demands, different high or low electrons that need to be transferred for each of the products that we may aim in such a process. And also we have to take into consideration that in aqueous system, always water undergoes reduction and is a competing reaction. So it always has to be taken into account. So catalysts are much more important than that are so much important in order to tailor exactly the overpotentials and actually have one of the desired products listed here. So why catalysts? Because at the different potentials one electrochemical cell is working, the catalyst has different interaction with the species that may be adsorbed, desorbed, or being created in the middle of the process. So the bonding strengths is essential, and the different potential that the system survives means that from all such complex mechanisms that may be followed, not all of them, but specific ones will be chosen or being actually realized. Each catalyst has a specific pathway to follow. The potential will even change that. If we look at this figure here to the left, to the y-axis, we see actually the selectivity of the production. And there are major products beyond the 10% selectivity and products with less selectivity, lower than 10%. If we focus also on these, we will see that even if we tailor the catalyst, we still can play with the balance of what is produced and at what selectivity is produced in a system. So you can see ranging from low to higher potentials that hydrogen dominates at the beginning, but as the potential increases, hydrogen selectivity goes down, allowing other elements like formate or methane to increase in the production. And then it's not a one-way process, so one-way procedure. So in a higher potential, again, hydrogen still dominates. It's actually the easiest reaction that can take place. It's this competitive reaction. So we can tailor our system with the electrocatalyst and with the potential, meaning the operating point of the cell that we choose to work with. Now, any kind of cell, we see here basic technologies categorized in two major, let's say, categories, the high temperature and the low temperature one. Please keep in mind that in any kind of cell, you need at least three components, 2 electrodes and an electrolyte. In the solid oxide electrolysis, excuse me, I just went one more back, okay. In the solid oxide electrolysis, we usually work with ceramic-based materials. We are in a solid system, we work with temperatures defined by the electrolyte, which is an oxygen ion conductor, and the range is approximately from 600, 700 to 900 degrees C. So this system of handle gaseous, obviously, flows, and they operate in high temperature. I will discuss about this high temperature a little bit also later on. We have the molten carbonate electrolysis, where a melt of carbonate like lithium oxide and lithium carbonate is used as electrolyte. This technology faces issues having to do with melting of alumina, zirconia, platinum, and so on in this electrolyte. So stability is an issue, and does not present technology which is highly used and applied. And moving to the interesting part of the low temperature ones, these two different configurations show a case where CO2 is provided in a gas diffusion electrode, meaning that is provided in gas phase. It can actually be fed by CO2 as gas, but keep in mind it allows efficient diffusion and so on. Therefore, gas diffusion electrodes are quite efficient. However, you have to consider that just one step before this, you need to have the CO2 ready from your capture process, released in a way to be fed here. So there is this cost of releasing the CO2 from the capture process. This is the most typical, let's say, cell, the H-type cell, where you have your electrodes, you have the catholyte and anolyte, which are liquid flow. So you have your CO2 here in your liquid flow. And different variations of membrane are suitable for the different, let's say, products that we aim. In a reuse project, we will try to make the best of the low temperature configurations by using liquid flow with higher concentration, because when you discuss liquid flows, concentrations are defined by the solubility of CO2 in the media. So we will try to increase CO2 concentrations in a liquid feed, but we will use diffusion layers or diffusion electrodes to minimize issues having to do with mass transfer. Now, just a little bit more in comparison between high temperature and low temperature, what would be the interest in choosing one of these technologies and why? Definitely, if you see thermodynamics, you have a total demand of energy, and as long as you move to higher temperatures, the electric demand goes down and the heat demand can meet the total requirement. Therefore, actually, you deliver less electrical feed in these systems than in low temperature ones, where you need to go to almost totally, not almost, practically there is no other feed than electrical energy. Regarding kinetics, if you go here, you know that low temperature compared to high temperature, the kinetics is favored in with temperature. Also, you can see here the two main, let's say, categories, how they are placed in the current density, representing the production rates, and the voltage here representing the energy you pay for this. So you can see that high production rates with low demands, this is the solid oxide technology, high demands and lower production rates for the low temperature technologies. And what does that mean also in terms of costs? Capital cost, as soon as you have high productions, your capital cost is less for a certain output. And also, if you minimize the operation cost, you refer to the voltage, which is less in case of the solid oxide. So just for comparison. As we already discussed, electrocatalysts are defining the products, are defining, are tailoring the pathway of the electrochemical reactions. So there are 4 distinct classes of metal catalysts for low temperature CO2 reduction in a typical media. You can see here for the different, let's say, products that we aim, which are the most suitable materials, metals to choose as your catalysts, your cathode catalysts. In reuse, since we aim in formic, tin is a key element for our application. A modified tin-based catalytic system will be employed. Now, I think I will shift a little bit just to comment for the formic acid, an example, how important it is to tailor not just the catalyst, but also the configuration of it. You can see here how a carbon nanotube coated gas diffusion electrode with a surface bound iridium princer dehydrate catalyst is used, in order to aim to formic acid production, tailor it. And you can see how this specific material is performing in a selective way towards our desired product. You can see here the blank experiment when argon is introduced in this in the cell, and you can see here the reaction, the reaction rate, the current actually when CO2 is introduced. So this tailored catalyst exhibited high efficiency and selectivity, and another aspect which is important, longevity for the production of formate, reaching a value which is suitable for this application, however, still quite low for high level implementation. Now, a little bit more on the solid oxide electrolysis, and I will say a few words about it because it's also a part of the work that we do in the lab. Why solid oxide electrolysis? If you just see the temperature, this is too high and it has some implications in terms of the materials, but it has advantages because you can have a feed of gaseous CO2 directly from any source. It allows efficiencies of very high efficiencies, excuse me for this, because of the temperature and because most of the energy is given also as a heat load, and it couples well with processes like refineries or the industries where metal industries where high heat loads are available to be used. Additionally, co-electrolysis can take place. So if you focus on this one, you have a single step process to produce white syngas as soon as it is powered by renewable. And you can actually tailor the syngas ratio produced by adjusting the operating parameters. So this is a typical cell and how it works. These are the reactions that take place, electrochemical and chemical reactions. And let's focus on this bottom right figure, saying that if we use different, let's see, different ratios of CO2 and steam in the electrolyzer, you can see here, you can upgrade them to CO and hydrogen ratios like these and tailor it so that they are suitable for your targeted product in a later step, a subsequent catalytic reactor that can do the conversion to the desired product. So overall, this is a highly promising CO2 technology, a power to syngas or a power to X scenario to be realized. You can see what I just mentioned about tailoring. So for different temperatures, you can see different current densities, but also for each current density that you have, you can actually tune from lower to higher CO, hydrogen to CO ratio. So you have a single step reactor that can give you tailored syngas concentration. In our lab, we actually work on tailoring novel materials to replace nickel metal basic state-of-the-art materials which are usually present in such technology, and to allow a much more flexible operation both for steam electrolysis or steam and CO2 co-electrolysis, or even the reverse operation, which means a fuel cell, and a class of materials that allows also ease of the system, because it does not really care, because it does not change due to its redox stability, its current state, even if you have a reducing agent or not in the feed, and producing decent to high current densities for such a technology. I won't go into the details and saying why it's so important to survive without hydrogen in the feed, because it will take too much time. I just show you here our champion material that has been developed and studied in the lab for years. So this is overall how one co-electrolyzer or a solid oxide electrolyzer overall can be implemented in a system, and downstream have a methanation reactor or a methanol synthesis reactor, and actually deliver renewable fuels from CO2. And coming to this last part, some advantages of electrochemical CO2 conversion mostly focus on the low temperature part. So one thing is that the process is completed without needing other oxidizing agents or any reducing agent, because what is done by gaining or losing electrodes at an electrode. This is the electrocatalyst, and you don't need more. So this is an important thing. It's simplicity and not just that. Without adding these oxidizing or reducing agents into the solution, then the consumption of some touches is reduced, and some side reactions, which are usually not desired, can be greatly reduced. Products can be controlled not just by the usual parameters like temperature, pressure, whatever, but also from the current and voltage. This parameter is crucial. Of course, the metal electrodes, the catalyst that we said already, and the electrolytes, the component itself. So you have an additional controllable variable in your system with this one, and you can actually tailor your products. Usually also, due to the configuration, the separation process can be simplified. So you can end up with high purity products. Exactly because of this control of the current and voltage, reactions that may not occur under usual conditions can be carried out through electrochemical pathway. And I will just bring the example of water splitting, water electrolysis. It cannot be done in low temperature, in room temperature. But if you apply potentially, if you sacrifice electrical current, electrical power, then you do have water splitting in room temperature because of the electrochemical reaction. Exactly this, usually, because I was mentioning about the low temperature one, these need ordinary temperature and pressure. So there is no extra energy demand for these, for any high temperature or high pressure. We don't discuss about the high temperature electrolysis here. This is another thing, but we did mention the benefits of it. Also, the electricity used to drive the process can come from intermittent renewable sources. Therefore, it's a very viable and sustainable pathway, and suitable also for large-scale power energy storage. And overall, these systems are compact, are modular, and they can be tailored on the demand and easy for scale-up applications. Of course, there are challenges, and we know them. As long as we discuss low temperatures, we discuss low kinetics, and even when the catalysts, the electrocatalysts, are suitable, still there are some issues that need to be tackled. Better electrocatalysts, more active, to be applied in order to meet the demand, to beat the slow kinetics. The selectivity is a significant issue, and again, properties of the catalyst, selection, engineering of it meets such issues. Energy consumption is anyway present, and it's important, it's substantial. So the biggest challenge is exactly how to minimize overpotentials that I started my presentation with this thing, the overpotentials that dominate the energy that we need to, the energy penalty, let's say, for the process. So as long as our catalysts are of high performance, then we minimize the overpotentials and we have a gain in energy consumption. Finally, the low energy efficiency of the process due to parasitic or decomposition of the solvent itself. So this needs also to be tackled in order to have selective and high efficiency processes towards desired products. So optimizations and research directions that will meet such optimization are listed here. These are actually the answer or the ways to answer the ones that I have already mentioned a few minutes ago about the challenges. And of course, scaling up. And with this, I will close and thank you. I hope I have no idea if I'm in time or not. So thank you for your attention.
Thank you very much, Stella.
Okay, I'll
Yes,
stop
meanwhile,
sharing.
as usual, if you have any question for Stella regarding the presentation that Stella just shared, if you have any additional insight, comment, question, please do so in the Q&A box. Milica, would like to take over?
Good afternoon, everyone. My name is Milica Milić, and I am a postdoc in the company Novonesis in Denmark. And typically what I do is enzyme immobilization, but today I will be here with another topic. And essentially, I'm here to talk about how do we reconcile innovation and ethics, mostly related to using enzymes and enzymatic carbon capture. So to begin with, actually, ethics is something that should ideally encompass all of our lives, and that when we, as human beings, not only as people who are maybe working in research, be it academia or in a company, we should be driven by ethics. And in general, there are the so-called 4 postulates or 4 ethical principles in innovation that should be respected when introducing a new process, a new product, a new service, whatever. So the first concept is beneficence, or basically doing things for the greater good. And in the sense of we drive innovation so that it helps people. On the other hand, there is also non-maleficence, which means doing no harm to people. And this is also reflected in a way that you should obviously not do harm to people, the environment, animals in animal testing, etc., etc. Then we have the concept of autonomy. Are people's rights respected? Meaning that you cannot just, let's say, build something on in a territory of one country without the consent of people who live there, or having good safety measures in your production line. And in the end, justice, last but not least, which kind of deals with the question, isn't the new technology fair and equitable? Basically, is it potentially available to everyone and not just to the privileged? So if we think about the time that we are living now, technology is advancing at an enormous pace, like never before. If you look at, for example, our phone today, 10 years ago, and then 20 years ago, you can imagine that this is a very exponential curve of development. And that somehow, I think that we have adopted new technologies, some, I would say, older generations, maybe with skepticism, but people who are more millennial, Gen Z, are just accepting them and then thinking about the consequences a bit later. Not necessarily the consequences, but what ethical implications it carries. So if you think about, for example, ChatGPT, I can use ChatGPT to give me a meal plan for the whole week, but I'm also feeding it information about my habits, my height, my weight, when do I go to work, when do I come back, and where is all of this information ending up in the end? And can it potentially be misused? Then if we talk about autonomous vehicles, self-driving cars are already a reality in San Francisco, for example, but there always comes the question like, will this car run over another person to protect you as the passenger? Then when we go into tech and data privacy, the infamous Facebook Cambridge Analytica scandal, where the data of users was actually used to kind of influence the US elections. Gene editing, very good to cure someone from a debilitating disease, but where do we draw the line of this? And so much more. And one of these topics is also green energy, which carbon capture is a part of. Now, if we go back from the more dystopian scenarios, ethics when doing research is more than that. It's obviously, I will not even go into it, not faking data, but it's also, for example, ensuring health and safety measures for both your customers and for the people who are working in your production line. So for example, with enzymes, and we will learn about enzymes in a couple of slides, they are proteins, and like other things, like other proteins, for example, pollen, they can cause respiratory allergies, which you might hear from my voice that I am a victim of. And basically, maximum safety measures are taken when producing certain products. Then it is also very important to recycle biomass to the maximum with the goal of actually minimizing throwing away something that could have been made into food, if not for humans, then for animals. Then it's also, if we come back to the non-maleficence, do no harm. If you can't do something good, then maybe not contribute to the bad. So, for example, most of the production in Novonesis runs on 100% renewable energy. And all of this is, of course, done in alignment with the EU net zero goal of 2050. But now that I mentioned enzymes for the first time, I would like to briefly introduce you to what enzymes are. And essentially, even if you don't know it, enzymes are a part of your everyday life. And moreover, outside of your body, they are mostly made by Novonesis, actually. So if you go about your day and do your regular chores, you will come into contact with enzymes more times than you think. So if you had yogurt for breakfast, enzymes. If you bought bread in the bakery, probably it's so fluffy and well risen because of enzymes. If you washed your clothes today, the component that actually makes your clothes softer and removes the stains are enzymes. If you go to a drugstore and buy some probiotics, supplements, even some drugs or skincare, the product was probably made using enzymes. And finally, if you just go and relax with your friends and have a glass of beer or wine, you guessed it, enzymes were involved in this. But what are they? I already mentioned that they are proteins and that they act as catalysts, which means that they speed up processes in living organisms. And essentially, when we eat food, for example, digestion already starts in the mouth, where different enzymes start breaking down starch, protein, milk into nutrients that our body can now take up. And as they speed up processes, they also accelerate chemical reactions. They're typically very efficient in small amounts, and they are highly precise and specific, so they can target one chemical group or residue and perform their reaction on that. And also, most importantly, they are non-toxic because they are completely biodegradable and soluble in water. And as they generally operate at very mild conditions in terms of temperature and pressure, they reduce the consumption of energy and they remove the need to use harsh chemicals. So apart from making things, enzymes can also be seen in, as I said, detergents. They're used to make bread that can stay fresh for longer, so they eliminate food waste. They are also used to remove pesticides, which typically end up in the water, in the soil, then water that we drink. And to our interest, they can also be used to produce green fuel and help make green processes. So coming to enzymatic carbon capture, I will just, you have heard, I would say, a lot in this presentation about carbon capture itself, but I would like to kind of add the word enzymatic to it and explain what that means. So as it was mentioned, carbon dioxide is, if you also think about sparkling water, it's not very soluble in liquids. So the absorption rate is not that high in water especially, but in organic solvents, it's a bit better. However, if you add one enzyme called carbonic anhydrase to the mix, this enzyme can take up CO2 from the gas phase, which is air, or the flue gas from the exhaust of factories, and transform it into the bicarbonate ion, which is then soluble. And carbonic anhydrase is one of the fastest known enzymes to man. So it dramatically increases the CO2 absorption rates. And as we've learned 2 minutes ago, as enzymes operate at mild conditions, there is no need to have very high temperatures, and they work at ambient pressure, which results in lower energy consumption overall. Now, the benefit is also that they are very eco-friendly and non-toxic, and that this system can be easily integrated into existing CO2 emission sources. And also, it has been shown that carbonic anhydrase, because the process is also, if you see the double arrows, means that it's reversible. So the enzyme also can aid desorption, which is essentially when we want to take this CO2 and remove it from where we captured it and then use it to make further products. So all in all, enzymatic carbon capture is great, but of course, like with everything, come a few questions. So the ethical considerations when using enzymatic carbon capture and carbon capture in general is basically whether this process is reserved kind of for wealthy countries. I mean, to be honest, I'm sitting in Denmark, and here I would say that it's quite easy to implement things like this. But the biggest consumption of fossil fuels is actually in countries that are not that well off, and they are in a vicious circle very much affected by the consequences of that. So there is always this question called climate justice. Should this be widely available? Now, there is also always, when there is a new solution, the question of intellectual property. So who owns the solution, and whether other people are supposed to buy this or get a license to use it, especially when it's something done for the greater good. And there is always the question of what is called informed consent. Basically, how much should the local community be involved? So let's say I decide that I want to build a CO2 capture plant in my neighborhood. Do the residents who live in my municipality also get to choose whether I can do that? And I would say that the highest not the biggest problem, but the biggest controversy around carbon capture in general is when you ask the public, they would say, oh, this is just greenwashing. So mostly who is driving the research in carbon capture are factories that are definitely using fossil fuel or producing excess CO2. So if we want to move away from fossil fuels, are we just buying time with carbon capture? Because if we were using some renewable resources, then this whole thing would not be as necessary. However, obviously, there's two things here, that carbon capture can be used for all sorts of processes, not only fossil fuel-based ones, but any process that results in combustion of CO2. And on the other hand, we as a civilization are just not at the moment that we are ready to cut off fossil fuels completely. Because if we stopped using fossil fuels this instant, 50% of all production in the world would just be cut off. Many people would not have electricity, heating. It would just be hell on earth. So this is the future, but we are not there yet. And also there is always the question of sustainability, because innovation is sustainable when it's also ethical. And the idea behind this is, well, is this process in itself sustainable enough that the costs and all of that which you put in outweighs the damage that pushing out CO2 will do? And I will say that it does. And naturally, as with other things, this technology is what I call a star on the rise. So yes, maybe we don't have the complete answers to every question, but I think that this is something very valuable and very much a step in the right direction. So as we go and as we evolve carbon capture, especially enzymatic carbon capture, which is something very new, the answers will come. With this, I would like to end my presentation, and of course, I invite you to write questions in the QA box.
Thank you very much, Milica. Martha?
Yes, thank you, Lynn. Can everybody hear me well?
Yes.
Thank you very much. Can you see my shared screen?
No, not yet.
Okay. But you should see it now.
Yes.
Wonderful. Okay, welcome everyone. Last but not least, thanks for being here. Still 100 people. My name is Marta Bissmann. I work for Clean Energy Solutions from Vienna, and we also have an office in Bulgaria as research coordinator. I want to thank my co-editors from Clean Energy Solutions, Plamen and Daniel, for jointly developing this presentation. Today, I will provide an overview of carbon capture, utilization, storage, and regulated regulatory and implementation aspects in the former European Union Eastern countries, and focus on Bulgaria. The European Green Deal sets the goal of climate neutrality by 2050, with an interim 55% reduction of greenhouse gas by 2030, greenhouse gas emissions. See Annex 1 of this presentation for more EU general legal basis and promotion initiatives of CCUS. CCUS is one of the measures to reach this political target, especially for the hard to abate sectors. By 2050, the European Union aims for net zero emissions, implying a need to capture and store or utilize CO2 that cannot be eliminated through other measures. The former Eastern EU countries, you can see here in this table listed, contribute about 25% of the total European Union greenhouse gas emissions. So they are key to Europe's decarbonization efforts, while still the Western European countries like Germany, France, and Italy are the main emitters of CO2. The energy supply and industrial sectors hold the highest potential for CO2 reduction via CCUS, with a combined theoretical maximum of 305 million tons CO2. For CO2 utilization, the estimated realistic potential amounts to 173 million tons CO2 within the EU 27, which equals to a potential of 1,730 potential CCU plants. To remind us, the reuse project focuses on utilization only. The share of CO2 reduction potential in the former 10 Eastern EU countries by means of carbon capture and utilization is 43 million tons CO2. This table presents a breakdown of the realistic product generation potential from carbon capture utilization. It is 50% for synthetic fuels, 42% for chemicals, and 8% for building materials. In the 10 former Eastern EU countries, the conversion potential for chemical products alone is estimated at 18 million tons of CO2. This slide provides a technology overview of the main CO2 sources used in CCUS applications. In the context of the reuse project, the focus is on biogenic single-point sources. For example, CO2 emissions from the combustion of biomass. These are particularly relevant as they can support carbon negative value chains when combined with permanent storage or reuse. This slide shows a CO2 capture technologies overview. The reuse project aims to capture CO2 from combustion, more precisely post-combustion, using absorption as main technology. Within the reuse project, we focus on electrochemical CO2 conversion, primarily aiming to produce carbon monoxide and formate acid as key output products. These products are valuable intermediates for synthetic fuels and chemical applications. For more detailed information on the full range of CCUS technologies, please refer to Annex 2 of this presentation. Here you can see some of the ongoing or completed CCUS projects in the former Eastern EU countries like Poland, Latvia, Czech Republic, whilst Poland being the most active country. The Bulgarian carbon capture and storage project will be presented in the next chapter of this presentation. Now we would like to move on to Bulgaria and highlight the situation in this country. Bulgaria is one of the most carbon-intense economies in the EU. It has the highest GHG emission intensity per unit of GDP in the European Union. The main emitting sectors in Bulgaria are energy, cement, and chemicals. And these sectors are emitting approximately 45 to 53 million tons of CO2 equivalents annually. Previously, the EU has been very active to publish directives, laws, and funding initiatives to promote CCUS development. See Annex 1 of this presentation. However, in Bulgaria, besides the Carbon Storage Directive, which was adopted in 2009, up to date, there is no dedicated national CCUS strategy or regulatory framework in place. In Bulgaria, the focus today is clearly limited to CO2 storage, so CCS. The CO2 storage capacity in Bulgaria is estimated for 2.6 gigatons of CO2, mostly in deep saline aquifers, coal formations, and depleted gas reservoirs. This could theoretically store nearly 80 years of Bulgaria's current emissions. The flagship project ANRAV is the first full CCS value chain project in Eastern Europe. It captures CO2 from the Devnya cement plant and it stores it in the Galata gas field. It will reduce 95% of the plant's emissions, which is 7.8 million tons CO2 over 10 years. This project will become operational in 2028. Here you can see the intended development phases and rollout of the CCS flagship project in Bulgaria. By phase 3, the system will scale nationally, integrating emitters, CO2 emitters from all over the country into that CO2 capture network of ANRAV. So what are our conclusions from this analysis of the Eastern European country situation and Bulgaria, the policy framework? The 10 former Eastern EU countries emit 25% of EU's GHG emissions. So the region offers very high CO2 reduction potential via CCUS. And several CCUS projects are already underway. However, the EU regulations still need to be fully adopted at national level to drive the development. In Bulgaria, the absence of a national CCUS strategy and regulatory framework is slowing down the development. To accelerate the CCUS development, Bulgaria needs to establish a comprehensive national strategy with clear targets, develop the necessary infrastructure, implement supportive regulations, and set up the domestic financing tools. Also, governance support and institutional capacity building, also from external, are critical. Thank you for your attention, and I'm looking forward to your questions.
Thank you very much, Marta, for your presentation, and also thank you for all of our speakers today. I hope everybody had a very nice and insightful session for today. We are very glad to receive a lot of questions from you, and we hope we tried our best. We tried our best to answer as many questions as possible. But if you, meanwhile, if you still have any questions that we do not have the time to answer today, please feel free to connect with us on LinkedIn with the QR code on the screen. And we are very happy to answer any questions you may have in general about reuse project as well as about the webinar today. And just a little bit of some updates about with relation to reuse project before everybody leaves. We are very pleased to have our presence at the EUBCE, European Biomass Conference and Exhibition 2025 happening in Valencia in Spain. If you're coming to the EU project exhibition areas, you will see us reuse project as well as many other European projects there, who are doing a lot of great work and a lot of great innovations with relation in different aspects in biomass. And another thing is that one of our project partner, who's unfortunately not with us today, Professor Walter Silva from the University of Aveiro, whom also a project partner of Reuse. He is presenting to a project poster also at the European Biomass and Conference exhibition. So if you're coming to the EUBC, you will also meeting Walter Silva individually. For all of this information will be, you can find all of this information on our LinkedIn page and also on our website. We will be updating this information in the subsequent days. So please visit our website as well as connect with us on LinkedIn. And another upcoming activities from our project is our exploitation workshop happening in a hybrid mode, both in person in Vienna, in the says a clean energy solution office address you can see on the screen. And also there is an online link available if you cannot make it to Vienna. So again, all of the details and information will be found online if you follow our LinkedIn page and visit our website. So once again, thank you very much, our speakers, for sharing great insights, and also for everybody who making the time to join us today in today's webinar. And we will disseminate all of the shareable informations and documents after the webinar. So please follow us and keep updated on our website and on LinkedIn. You will see some summaries and also some public dissemination level information about the webinar today. So thank you very much. And we'll see you in another event. Thank you.
Thank you all. Bye-bye.
Thank you.
Thank you all.
Bye-bye.
Bye-bye.
Thank you all.
Thank you.